Welcome to the lesson on section 10.3, Separable Equations. In this lesson, you'll learn how to solve separable differential equations. You'll see how to write a general solution and how to find a particular solution to an initial value problem. A differential equation is separable if it can be written in the form dy dx is equal to the product of a function of x and a function of y. In other words, to separate the differential equation into y's on one side and x's on the other, we should only have to multiply or divide. Consider the first example. Dy dx equals 1 over 3y squared minus 1. Start by using multiplication or division to separate the x's and y's on different sides. That can be accomplished here by cross-multiplying. Anti-differentiate both sides to eliminate the dy and dx. After anti-differentiating, we only need to write plus a constant on one side. Consider the c a combination of the constant that would have been added to the left and the constant that would have been added to the right. We don't know either value, so we can combine them as a single c. In the second example, dy dx equals 4x times the square root of 1 minus y. Separate by multiplying dx and dividing the square root of 1 minus y. Calculate the integral of both sides. To integrate the left side, I'd rewrite that as 1 minus y to the negative 1/2 power. And to reverse the chain rule there, I need a negative outside the parentheses. To make this happen, I multiply by negative 1 inside the integrand and by another negative 1 outside the integrand to balance it out. This is my way of skipping the u substitution. Anti-differentiating, I get negative 2 times 1 minus y to the 1/2 equals 2x squared plus c. The negative in front of the 2 comes from the negative that I multiplied outside the integral in the last step. Next, I'll isolate y. You might not always have to isolate y in your solutions. We didn't in the first example because it would have been very difficult. Look for directions like as a function of x as an indicator that you need to solve for y. I've omitted the directions in all of these examples, so we're just solving. First, divide both sides by 2. Notice that when I divide by 2, I don't bother writing c over 2 here. Since you don't know what c is, it doesn't matter. Square both sides and isolate y. So y equals 1 minus the quantity x to the 4th minus 2cx squared plus c squared. In example 3, dy dx equals e to the x plus y. To make this look more separable, I would rewrite e to the x plus y as e to the x times e to the y. Separate by multiplying by dx and dividing by e to the y. Take the integral of both sides, and the antiderivative is negative e to the negative y equals e to the x plus c. Divide through by negative 1 to start isolating y. Notice that it makes no difference whether I write this as plus a constant or minus a constant, since I don't know whether c is positive or negative anyway. Continue isolating y by taking the natural log of both sides. To get negative y equals the natural log of negative e to the x plus c. And then multiply both sides by negative 1. So y equals negative the natural log of c minus e to the x. In my last example, y prime plus 2y equals 0. Rewrite the y prime as dy dx and subtract to isolate the dy dx. Divide by y and multiply by dx to separate, and integrate both sides. I get the natural log of the absolute value of y equals negative 2x plus a constant. In exponential form, this means that e to the negative 2x plus c equals the absolute value of y. I can rewrite e to the negative 2x plus c as e to the negative 2x times e to the c. And since e to the c is all constant, it's customary to replace this with a single letter, typically a capital A. So the absolute value of y equals a times e to the negative 2x. Since I don't know the value of a, I also don't know whether it's positive or negative. So this means that I can eliminate the absolute value signs without changing the meaning of our solution. So y equals a times e to the negative 2x. In any of these examples, if we wanted a particular solution, we would have to be given a point that the solution graph passes through. So for example, if I had a point that our solution was supposed to pass through, I would plug those values in for x and y here, and that would allow me to solve for the value of the constant. This concludes the lesson on section 10.3, separable equations.